All right, we're looking at the area of a triangle and the area of a trapezoid. We're going to start with triangle. These are three examples that you're going to see in terms of what a triangle might look like. This one, of course, we learned is a right triangle because it has a 90-degree angle as one of its angles. This one you learned is an acute triangle because all of the angles are less than 90 degrees. And this one you learned is an obtuse triangle because it has an angle that's larger than 90 degrees. All right? And if I want to find the area of this, you could probably tell me by now that its area equals base times height divided by 2 or some version of that. So really quickly, we're sort of going to talk about why that's true here. So if I look at this first one, you can probably tell me that you know that the base is 1, 2, 3, 4. You know the base is 4. And that you know the height is 1, 2, 3, 4, 5. And you probably could even tell me that you know the area is base times height divided by 2. And that would be 20 in the numerator divided by 2, giving you an area of 10. Now, looking at the triangle, if we were going to count blocks to determine what the area is, we would say, okay, that's 1, 2, 3, 4, 5, 6. There's definitely 7 holes here, and then there's some partials here that I'm not really sure how much exactly of the square they are to get square area. And so what we do is we actually consider the entire rectangle that would have been created around this triangle. Okay? And this rectangle, of course we know, has an area that can be found by doing a base times height, because it is truly 1, 2, 3, 4, 5 down and 1, 2, 3, 4 across. And so I could see that it has an area of 20 simply by counting all of these squares and determining that it truly does have 20 complete squares within the triangle. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 squares in here. But I don't really want the entire triangle. I really only want, the entire rectangle. I really only want half, which is the triangle that we're talking about. So you can see easily there that I can take the base times height that would have been the area of the rectangle around it and just divide it by 2, and that gives me the area of the triangle that I'm interested in, okay? Which is just, of course, the area that is inside this triangle right here. So that's really, really easy to see when you're talking about a right triangle. Now, when we come to an acute triangle like this, seeing the rectangle isn't necessarily difficult, right? So I could draw a rectangle around this. But knowing that this part is actually going to be half of this, that's a little harder to visualize. Sort of why we convince you with a right triangle and then move it and say, okay, this is actually true of every single triangle. And I actually cut a note card for you where this piece fit right on top of this piece, and this piece would fit right on top of this piece. Okay? But that's neither here nor there, because regardless of how I find or see the rectangle, if I'm talking area of a triangle, I'm still really just talking base times height. I can orient this any way I want so long as I figure out which base I happen to be talking about. If you can find one that's horizontal, that's the best possible option for you. So this one has a base 1, 2, 3, 4, 5, 6, 7. I'm going to recount that one more time. 1, 2, 3, 4, 5, 6, 7. Good. So I've got a base that is 7. And I've got a height that is 1, 2, 3, 4, 5. Okay. A lot of times in geometry, you will actually see the height drawn from the tallest vertex of the triangle. and just drop down as a perpendicular inside. 1, 2, 3, 4, 5. But they're just measuring that highest part. I think it's easy to come outside and sort of see it, but you can see it inside as well. And then from there, I can find my area by doing base times height divided by 2. So we have 35 divided by 2. And unless I specifically ask for a decimal, you can actually leave it just like that. Okay? All right. This is the third kind. It's obtuse because one of its angles is bigger than 90. And again, we could sort of be convincing that if I could find this whole rectangle surrounding this triangle, I maybe could get half, but kind of unnecessary here. It's much more difficult to see where the rectangle would be in a case like this because I think it doesn't look at all and probably isn't half of that what I just showed you. So it's actually strange the way you would have to look at this. But again, neither here nor there because we convinced you the formula was true in the first one. So again, we would just want area of this triangle. So inside here, we're going to find a base, which is across the bottom here. 1, 2, 3. Our base is 3. And our height, you can come out here and sort of see here that our height is 1, 2, 3, 4, 5 again. See, all of these have a height of 5, even though they all look totally different. On IXL, what they're going to do is they're actually going to come to this very highest point in the triangle, the highest vertex, and they're going to come straight down and kind of create this right triangle outside the triangle to show you the height. But really, the height is going to be 5. Whether you see it over here or sort of see it over here, you can ignore that except you need that height in order to find the area of it. So your area is going to be base times height divided by 2, which is 15 halves. Leave it as a fraction unless you have to go to decimal. All right, following the area of a triangle, we're going to look at the area of a trapezoid. And they're sort of together because their formula is very, very similar. So imagine you have a trapezoid, and it looks something like this, right? And you want to find the area of it. Well, it should sort of hit you that this is really very, very close to a triangle, but kind of like missing this top piece, right? So the area of this is going to be quite similar to the area of a triangle, okay? So what we're going to do is what would generally be, and let me write it in pencil here so I can erase, base times height divided by 2 for a triangle, we have altered the picture. And instead of just having one base, we now have a bottom base, which I'll call B1, and a top base, which I'll call B2. So I'm talking this distance and this distance. So instead of just being base times height divided by 2, there's now not just one single base. We have a top and bottom base. So the formula needs a little adjustment. It's actually base 1 plus base 2 times the height divided by 2. And that becomes the area formula for your trapezoid. Okay, so if I wanted to find the area of this particular picture, then I would need to find the lengths. 1, 2, 3, 4, 5, 6. My base 1 is 6. And then 1, 2. My base 2 is 2. All right. And that would be 6 plus 2, which is 8. Then I would multiply that times my height, which is this distance, or we can come out here if you'd like, just from top to bottom, how high or how tall is it? So 1, 2, 3, 1, 2, 3, however you want to look at it. So this would be 8 times 3, which is 24, divided by 2 is 12. So the area of this trapezoid is 12. Okay, I will do one more for you. So this is almost a triangle. You can see just the top part is missing. And so the first thing we want to do is we want to add the two bases, then multiply the height, then divide by 2. So 1, 2, 3, 4, 5, 6, 7, 8 for base 1. And base 2 would be 1. So we would do 8 plus 1 is 9. And then we would look at the height of this. 1, 2, 3, 4. One more time. 1, 2, 3, 4. The height is 4. So 9 times 4 is 36. And then we would divide 36 by 2, and we would get the area is 18. Okay, I hope that helps.